Hi everyone, I am Krunal Chagani from BTech 2020 batch, DIICT. This is our project topic, quantum key distribution. Let's first talk about cryptography. So what is cryptography? Whenever there is a sender sending a message to receiver, their communication must be secure. Encryption is a method used in communication to convert plain text into ciphertext. And similarly, decryption is the message to convert ciphertext back to plain text. So here is a word hello, which is a plain text. We will use some encryption method to convert it into ciphertext. And then for that ciphertext, we will use decryption method to convert back into uh, plain text. There are two types of keys in cryptography. One is public key, for which is used for encryption of plain text into ciphertext, and one is private key, which is used for decryption of ciphertext into plain text. Also, there are two types of cryptography: symmetric and asymmetric. In symmetric cryptography, public and private key are same, but in asymmetric cryptography, public and private key are not same. So let's now talk about challenges in classical cryptography. First is data privacy. In traditional cryptography, the problem is of factorization of huge prime numbers that determines security of data in traditional cryptography. Since it is considered as a hard problem, like if we are given two prime numbers and we have to factorize them. But if we see quantum computers, then they can factor much faster than classical computers. Second is classical key distribution. Whenever someone is sending message to other person in traditional key distribution, someone in between the users maybe try to read that information. That tactic is called eavesdropping, and both the users will not get to know about it. They will not able to detect that someone is hearing their message. So this is the problem in classical key distribution. Yes. So eavesdropping. Here Alice is trying to send a message XAPA to Bob. In between them, Eve, which will intercept the message, she will try to read that message through classical communication channel. And it is the possible case that Alice and Bob won't know about it, that their data is being read by someone. Brute force attack. Uh, since there is low frequency of key updation in traditional cryptography, so brute force attack can success. Yes, key exchange. In traditional key exchange, it relies on mathematical problems that are considered to be hard, but quantum computers can solve that problems easily. So some people can find our private key using our public key. Yes. So now we'll see that how we can overcome these challenges by quantum cryptography. So data privacy. In quantum key distribution, any attempt of eavesdropping communication can be detected. Since there is a fact of no cloning theorem that a quantum state can't be copied. So if Alice is sending a message through quantum channel to Bob, and if Eve tries to read that quantum state, then she will make a copy of that and its state will be changed. So after that information will reach to Bob, it will be modified. Information will reach there. So it will be detected that Eve has tried to read some information. Now, key exchange problem. This problem can be solved by Heisenberg's uncertainty principle and no cloning theorem. No cloning theorem, we already saw that no quantum state can be copied. It will change its state. So US dropping will be detected in quantum key distribution, and we can overcome this problem. Brute force attack. We can modify the key, which we can't do in traditional cryptography, to improve security when a third party is attempting to intercept the message via quantum key distribution. Yes. So here also, there is a person who is sending message to other person, and if someone tries to hear or intercept that message, then they will both get to know about that someone is hearing the information or trying to read the information. Okay, so now let's talk about quantum key distribution overview. Uh, Quantum cryptography uses quantum key distribution, a key sharing technique to provide a totally random key for encryption. Yes, random key. It will use some quantum physics concept like no cloning theorem, Heisenberg's uncertainty principle to provide basis for this theory. And if we use this principle, a secret and random safe key can be created. With that key, we can encrypt and decrypt the data. And this QKD also enables that whether an eavesdropper is listening to our private conversation or not, using no cloning theorem. Yes, this is same that instead of classical channel, we will use a quantum channel and generate a shared key between Alice and Bob to share information. Through a quantum channel, an unauthorized conventional channel, Alice and Bob may safely exchange the keys. And either it is mode fiber or free space served as a quantum channel in this arrangement that we can see. Uh, loud, uh, this we will talk about next in our presentation, that how shared keys are generated. Okay, so now this is our problem statement studying quantum cryptography and quantum key distribution protocol, which will allow two parties, example Alice and Bob, to create a secret shared key via an unsecure channel. The channel, quantum channel, is unsecure because anybody can try to read that information, but we should be able to detect that somebody has tried to read our information. That should be kept private, and the likelihood of spotting any key manipulation or interception should be minimal, and we should be able to detect it properly. Yes, so these are some theoretical backgrounds that we will be needing for understanding quantum mechanics. First one is no cloning theorem, and second one is uncertainty principle. We already talked about it enough. Like it is impossible to make an exact copy of an unknown quantum state. It will change the quantum state if we try to do so that. Then superposition, like a particle can exist in multiple states simultaneously, is known as superposition. For example, a photon can have both states, horizontal and vertical, at the same time. Then entanglement, when two or more quantum systems become correlated in such a way that the state of one system can't be described independently of the state of other system. They said to be entangled. Otherwise, otherwise they said to be in product state. Quantum states and measurement, like if we have a quantum state, then we can measure it in some basis, and its measurement result will result into different outcomes with different probabilities. Yes, so we will study BB84 protocol. It is the first quantum key distribution protocol. Like if Alice and Bob wants to use classical communication channel to share their key, it is possible to tell if Eve has made a copy of this key herself. They must be completely trust Eve that she is not listening. Like if we are using traditional cryptography, then we have to trust Eve if we want to communicate through her classical channel. However, yes, so if Eve provides a quantum communication channel, Alice and Bob no longer need to trust Eve. They can share their messages independently. And if Eve tries to read that message, then they both will detect it. The protocol makes use of no cloning theorem of quantum mechanics, which states that we have seen that like quantum state can't be copied, and this is the circuit for that. Like if we try to do so, then it will not be possible. However, if we are using classical communication channel, then you can easily copy the bits that are transmitted through classical channel, and Bob and Alice would not be able to detect it. So these are some steps of the BB84 quantum key distribution protocol. So first step is Alice will choose some random bit string like the message that she wants to send Bob through Eve's quantum channel, and after that she will also choose a random basis for encoding each bit into qubit. Either she can choose from Z or X, and she will keep this information private to herself. Example, this is the bit string and this is the string of the basis. She will generate that qubit. Now Alice encodes that message according to her particular order of qubits. Uh, like uh, in this case, we can see that first qubit is 1 and it is encoded in Z basis, so it will be 1 only. And second qubit is 0. Likewise, third qubit is uh, 0 here and it is encoded in X basis, so it will be converted into plus state. This string will she will send to Bob. Now, when this message will reach to Bob, he also chooses some random basis for each qubit to measure it. It can be X or Z. And Bob will also keep the result as private. Like this is the example. Now, Alice and Bob will reveal publicly through use channel that in which basis they measured each qubit. And there are two possible cases. If Bob has measured a qubit in the same basis that Alice has prepared in, then they will use this part of information to form their shared key. And if that is not the case, it is different basis, then they will discard this information since there will be some mismatch. So in fifth step, Alice and Bob will make their part of shared key, and from that they will take a sample and they will try to compare that sample and see if their sample matches or not. If their sample match, then they will be sure that no one has read any information from the channel. And if their sample mismatch, then they can detect that you has tried to read some message through the quantum channel since its state is changed and their message are not matching. So this is violating no cloning theorem. So they will detect use interception. So this is the detailed example that we have taken. Suppose that length of the qubit is 10 bits and Alice will generate these random bits. First of all, these bits will be known to Alice only. So this table described that. Now Alice will choose some random bit string that in which basis she will prepare the qubit. So this is the string. Here 0 means she will prepare in Z basis, which consists of 0 and 1 quantum state, and for X basis it is plus and minus quantum base. She will also keep this information private to herself. Now in step 2, uh, we can see that if we have one state and we are preparing it in one basis, means X basis. So there is a Hadamard gate which will create 0 bit into plus state, and it will convert. Hadamard gate just converts 0 state to plus state. Similarly, we can see that we have fourth index as 1 bit. So for preparing 1 bit, we simply apply not get to 1. So if we apply not get to 0th state, it will convert it into x 1. It will convert it into 1 state. Now in this way, Alice will encode the message and send it through use channel to Bob. Okay. So now in step 3, Bob will also choose random basis from X or Z to measure that qubit and store the information. These are the Bob bases. Bob will keep that information also with themselves. Now we can see that Bob will measure incoming message through each channel, and if it is the same basis that he has chosen and Alice also chosen, then its probability of getting the same result will be 100%. And if both the bases are different, then it will give 50% 0 or 50% 1. So Bob's result will be mismatching with 50% probability. Here, this is the example for 0th index and 6th index. We can see that 0 bit is measured in X measure and 1 bit is measured in X basis for 6th bit. Now Alice sends all the bases through each channel, and Bob also sends his basis for each channel, and they both reveals that information publicly. If Bob has measured a bit in the same basis, then Bob's result will match with Alice bits, and if it is different basis, then their result won't be matched. So they will discard that bit. Here we can see that Bob and Alice will public their basis. Now, if they measure in same basis, then its result will be matched. So they will use that part of information to form their shared key. And if it is not, if they are not matching, then they will simply discard that bit. We can see that this is the Bob key and Alice key, and it is completely matching. Yes. So at fifth step, Alice and Bob will take a sample of fixed size and they will send it to use channel and they will compare that sample. Like here, when we can see that sample of 6 size and it is of 0, 2, 3, 5, 6, and 7 index, and we can see that all of the bits are matching. Yes. So if protocol has worked correctly without any errors, then both samples should match. So we can see that if there's simple match, then there is high probability that both the keys are same, and they can now form their communication reliably and use their shared key for encrypting the messages. Yes, here we can see that they will generate shared key and it will be known to Alice and Bob only. Eve's channel will not get to know it. Yes, this is a similar example with inception. So here Eve will try to read that information. So we can see that after this step, just like Bob measure it, Eve will try to measure. So it will change the state of the qubit according to no cloning theorem. And we can see that after that state is received to Bob, he will measure it with different probability. Since the state is changed, so he will get 0 with 50% and 1 with 50%. So its results will be mismatched only. So we can see that if we in the fifth step we take the sample of 5 size, then second bit is mismatching. So we can simply say that someone has tried to read that information and they will discard that result and transmit it again. So Eve's attempt of US dropping has been failed. Yes, so this is the risk analysis. We can see that there is a 50% probability of Eve choosing the different basis and 50% probability of Eve choosing the same basis. Now, if Eve chooses the different basis, then also Bob will measure the value L is prepared. In this case, US dropping will be undetected. And in this case also, in which Bob will choose the same basis as Alice has chosen. All of three have chosen the same basis. In this case also, Alice will send information to Bob and their information will be matched. So they will form a shared key, but Eve has tried to detect it. Eve has tried to read that information. So we can see that there are two cases in which there can be undetected transmission. So we can see that the formula for probability of Eve's going undetected is 0.75 raised to n, where n is the number of qubits. So we can see that as we increase the number of qubits, probability of undetectedness of Eve will decrease with the number of qubits. Yes, so this was the whole protocol. Thank you everyone.